Let's look at some examples of the image and null space of a linear map. So let's describe the null space and also the image of this linear map. And while we're at it, let's find its rank and nullity. We have to sort of decide what we mean by describe. Since we know null space, the null space and the image of this map are subspaces of R3 and R, I mean, how can we describe subspaces? One nice way to write a subspace is just to find a basis for the subspace. So what we can do is find a basis for the null space and a basis for the image. All right, so for this example, let's start with the image just because it's easier. Remember, the image is all of the outputs that actually come out of this function. You can see just based on the formula for this function that every real number is going to come out as this function. So the image of this function is all real numbers, right? All real numbers is a subspace of the vector space of all real numbers. So I guess that's not particularly interesting, but that does tell us what the rank is. Remember, the rank is the rank of a linear transformation, or a linear map, is the dimension of the image, and the image is clearly one-dimensional, so the rank of this map is 1. All right, so now let's look at the nullity and the null space. Remember, the null space is everything that this linear transformation sends to 0. So we need to know what vectors A, B, C produce 0 as outputs. So in general, in general, we would need to write down the result of this transformation and then set this equal to 0, right? What we're really asking about is what are the solutions to this equation. In general, this is going to be some system of linear equations, but for this particular example, it's pretty straightforward because this side of the equation, pi sub 2 of ABC, is just b. Right? So we need b to be 0, and a and c can be anything, evidently. So the null space of this map, pi 2, is just the collection of all vectors a, 0, c, and a and c can be real numbers. Okay, so this explicitly describes what the null space is, but we haven't written a basis for the null space yet. But that's not hard to do. In general, finding a basis might be tricky depending on the example, but for this particular example, this is clearly just the span of 1, 0, 0 and 0, 0, 1. And these clearly span this subspace of R3, and also they're clearly linearly independent, so these two vectors form a basis for the null space. Since we have a basis with 2 elements in it, that means that the nullity of this map, pi 2, is 2. All right. Incidentally, I'm calling this pi 2 because the pi is a Greek p for projection, and 2 tells you which entry you're projecting onto. So this pi 2 is just trying to imply that we're projecting onto the second entry, and sure enough, this map does just pull out the second entry of the vector. All right, for another example, let's describe the null space and image of this linear map. So this one goes from R2 to P2. Again, we'll describe the null space and the image by finding bases for them. For the image, right, the image is just everything that looks like this, right? So every polynomial that we can write as a plus a minus bx plus bx squared. But to find a basis for this, we have to write this as the span of linearly independent vectors, that is to say, linearly independent polynomials. But for polynomial spaces, we know how to do that. We can sort of group up terms that have a and group up terms that have b. So if we multiply this out and then group terms that have a, we get a times 1 plus x. And then if we group up terms that have b, we get b times minus x plus x squared. Okay, so the image of this map is the span of these two polynomials, 1 plus x and minus x plus x squared. These two polynomials are obviously linearly independent, and so the rank of this linear map is 2, because the dimension of the image is 2. All right, so now let's look at the null space and the nullity. So as with the previous example, we need to know when does this function produce 0 as an output. So the output of this linear map is a plus a minus b x plus bx squared. We want to know when is this output the 0 polynomial. Well, a polynomial is equal to the 0 polynomial only if all the coefficients are equal. So we can turn this into a linear system. A has to be equal to 0, because this first coefficient has to be equal to 0. The second coefficient has to be equal to 0, so a minus b has to be equal to 0. And the last coefficient has to be equal to 0, so b has to be equal to 0. So both a and b have to be 0, right? So the null space of this map, right, is all of the polynomials, or sorry, all of the vectors in R2 whose first and second entries are both 0. In other words, the null space of this polynomial is just the trivial subspace with only the 0 vector in it. Then the nullity of this map is the dimension of this subspace, but the dimension of the subspace of only the 0 vector is 0, right? This is a 0-dimensional subspace. All right, so the rank of this map is 2, and the nullity of this map is 0. Last example, I think this was the last example, the null space and image of this map. So this one is going from a matrix space to a Euclidean space, so from M22 to R3. So for the image, right, again, to describe the image, we need to express all outputs as linear combinations of linearly independent vectors. Since our outputs live in a Euclidean space, we know how to do that. Just break this up, parameterize these outputs as using vectors, right? So this is a times 1, 1, 0 plus, let's see, there's b times minus 1, 0, 1 plus d times looks like 0, 1, 1, right? So where I'm getting these vectors from is I'm just looking at the coefficient for the vector multiplied by a. I'm looking at the coefficients for a, right? It's 1 here, 1 there, and then 0 for this last one, so 1, 1, 0. And then similarly for b, it's minus 1, 0 for the second one, and then 1 for the third one, and then similarly for d. So that's where those vectors are coming from. All right, so these three vectors are clearly linearly independent, maybe not super obviously linearly independent. If you're not sure if they're linearly independent, you should check. They are, though. I think. Pretty sure. I don't know. Maybe I should do it. So this might be something to fast forward, but to check linear independence, we just need to row reduce this, right? So let's maybe subtract the first row from the second. So 1, minus 1, 0, 0, 1, 1, 0, 1, 1. Oh, okay. Actually, I spoke too soon because it looks like these are linearly dependent. So we don't actually need all of these, right? Because now, next step of row reducing, we can zero out this row. Okay, so that means we don't actually need all three of these. We can discard. The pivots tell us that we need the first two, so we can discard the third one. Okay, so this is actually our image, right? So this writes we have a basis of our image. So that means, so the image is, right, the image of this linear map is the span of these two vectors, 1, 1, 0 and minus 1, 0, 1. And these vectors are linearly independent, so this shows that the rank of this map is 2. All right, now for nullity, we need to know what is the null space of this. So we need to know when is the output of this function 0. So take the output of this function, a minus b, a plus d, b plus d, set this equal to 0. And right, by 0, I mean the 0 in this codomain space. So that's 0, 0, 0. All right. So we need to know. So we need to solve this system of linear equations, right? This is really the system a minus b equals 0, a plus d equals 0, and b plus d equals 0. And we have to keep in mind that c, even though the variable c doesn't show up in these equations, it is a variable in the system, even though it doesn't appear in any of the equations. So when we do a matrix row reduction to solve this system, we have to include a column for c. So the first equation is 1, minus 1, 0, 0, and then 1, 0, 0, 1, 0, 1, 0, 1. Okay, and of course, right, this, if you look at the first, second, and fourth columns, this is essentially the same as what we did up here. So we already know what this row reduces to. It row reduces to the same thing, except we're going to have this extra column of zeros. So we get a 1, a column of zeros, and then 0, so a column of zeros, and then 0, 1, 0. Okay, and all of these entries are also 0. Okay, so right, this tells us now we can parameterize the solution set to this system of equations. We know that, so A, B, C, and D, and that's a D. We know that A has to be 0, B has to be minus D, C can be anything, right? C doesn't show up at all, so C can be anything, and then D is free, right? C and D are free, so both C and D show up in our parameterization, and then parameterizing this vector style, we get C times 0, 0, 1, 0 plus D times 0, minus 1, 0, 1. Okay, these two vectors are clearly linearly independent, so the null space of this map is the span of our domain space is this matrix space. It's not R4, so I shouldn't be writing this. I should write it like they're 2x2 matrices, because they are 2x2 matrices. So this should be C times 0, 0, 1, 0 plus D times 0, minus 1, 0, 1. There we go. Okay, so the null space of this map is spanned by the two matrices 0, 0, 1, 0 and 0, minus 1, 0, 1. Okay, these two matrices are clearly linearly independent, so we have a basis for the null space, and that means the nullity is just the number of basis elements here, so that's 2.